Now, we as software developers, we don't actually deal with those low-level hardware-based solutions, but they are actually used as building blocks, as we said, for higher-level software-based tools. So the first one is a mutex lock, okay, and mutex stands for mutual exclusion, okay. It is a simple variable, Boolean variable, okay, that we are testing whether or not it's available. So the calling process will test the value of lock. If it is available, it will be allowed to enter the critical section, but then it sets it to unavailable, which means any other process will now be prevented from entering the critical section until the currently executing process will set it back again to unavailable. Okay, so then this is what the solution will look like. In the entry section, a process will acquire the lock, it will enter the critical section, and then in the exit section we are releasing the lock. Okay, so when we have a process P0 here in the critical section, if we have a process P1 in the entry section trying to acquire the lock and it finds it unavailable, then that process moves to the blocked stage. Remember, we talked about the processes state, and when a process is waiting for an unavailable resource, this is an example of it. Okay, so this process will be moved to the waiting queue or to the blocked queue until the lock is available again. So this is what acquire and release look like. So release is simply setting available to true again. Okay, this means that I'm done executing the critical section and I'm releasing the lock. I'm making it available again. Now for the acquiring, as we said, you're simply checking for the availability of the lock. As long as it's not available, you are waiting. Okay, now there's two variations of the mutex lock. There's the spin lock, which we can see right here. You can see that as long as the mutex is not available, the process keeps spinning in this busy wait. That's why it's called the spin lock. So the process will not move to the waiting queue. It will still be in the running state, but it's not doing anything useful. It's just spinning in this busy waiting loop. Okay. And then, of course, once you acquire the lock, you have to set it to false to prevent any other process from entering the critical section. And these two instructions are atomic. They cannot be interrupted. Okay. Okay, so we said that these software-based synchronization tools are built upon things like the compare and swap hardware instructions. So to implement the mutex lock, we have to initialize the lock, and this is the so we'll be using the POSIX pthread library, and this is how to initialize the lock. And this is the acquire function. It's called pthread mutex lock, and this is the release function. It's called pthread mutex unlock. Okay. The second software-based tool is the semaphore. So the semaphore in its basic format, which is called the binary semaphore, it acts really similar to the mutex lock. Okay, it's simple. It's a simple integer. Okay, a binary integer that gets set to 1 when it's available and 0 when it's not, right? And then to acquire it or to wait for it to become available, you use the wait function, and to release it, you use the signal function. So previously they were called the P and V functions. This is what it looks like. So the wait function, or what is similar to acquire, again, it looks very similar. We have this busy loop right here. As long as the S is negative, then we do nothing. So we're waiting for another process to signal it, which simply incrementing its value to 0 again. And then once you acquire it, you are making it unavailable for others by decrementing its value. Okay, so if it's positive, if it's 0, this means that this is available. If it's -1, this means that it is not available. So this is what we've just talked about, the binary semaphore. Now there's more complex type of semaphores, which is the counting semaphore. I'm not sure if I have a slide about it. No? Okay. So the counting semaphore is simply integer values that keep incrementing with more calling processes and more available resources. So let's say we have 3 printers, right? What we can do is have a semaphore, a counting semaphore. So it keeps increasing with more resources we are using. So let's say P0 comes in, we increase, we set the semaphore to 3, right? So when P0 comes in, we have all the 3 printers available. So now P1 uses the first printer and the semaphore is 2. And then we have the next process, it uses this printer, now the semaphore is 1. And then we have another process that uses this printer, and now the semaphore is 0. When a new process comes in, then it's going to detect that we have none of the resources available, so now it waits. So all the other processes now will simply be waiting in the waiting or the blocked state. Okay, this is the counting semaphore. Now, semaphore has also more flexibility as it allows us to skip the busy waiting using some more sophisticated methods, and that's using the struct function and the linked list. So instead of making the processes spin in busy loops, we can actually add them to a waiting list. So whenever a process finds the semaphore unavailable, it will simply be added to this linked list using this block operation. And then once the semaphore is available again, it gets woken up using the wake up function. So this is the implementation of the wait and signal now. This is a new implementation. So the wait will simply decrement the value of the semaphore. If it's negative, we're simply adding the process to list and applying block. And to signal it, to release the semaphore, we are increasing its value and removing the process from the list if it's currently waiting. So in pthread implementation, there's 2 types of semaphore, the named and unnamed. Okay, so the named semaphore simply means that we give the semaphore a name, and then all processes can use this semaphore and share access to it. They're simply going to call it by name. And this is the wait and signal functions under pthread, so it's called semWait and semPost. For the unnamed semaphore, now only the threads that share, only the threads within the process can access the semaphore, but no other outside process or outside thread can actually access it because it's unnamed. It doesn't have this global name. Only those local threads to the process can use it to synchronize. So this is the wait and signal functions. Now, the problem with the mutex lock and semaphore is it depends highly on the developer and its knowledge and skills. So if we have a beginner, for example, an experienced developer who writes something like this, so signal, mutex, critical section, then wait, you can see that you are actually releasing the mutex, entering the critical section without waiting for the mutex. So all processes can actually just enter the critical section at the same time without any protection, because we failed to put the wait of the mutex in the beginning. And similarly, if we do something like this, if we have 2 waits, so you are acquiring the mutex, entering the critical section, and there is no release, right? So again, you are acquiring it again. So this process will be blocked here indefinitely, and then all the other processes will be blocked as well, because they're waiting for this mutex that the process who's currently holding it is not releasing it. Okay, so you're gonna end up with a deadlock situation. Now, to solve that, there is more sophisticated tools like monitors. Okay, so the monitor is like this high-level abstraction that give us the mutual exclusion for free. Okay, so it's like a package right here where you put all your shared variables in here, and internally it comes with the different functions and procedures that manipulate the shared variables. So you cannot access this shared data from outside the monitor. Okay, you have to use just these local functions to manipulate these shared variables. Okay, and as we said, only one process can enter the monitor at a time, which means we have mutual exclusion. This is one very simple monitor. So we have the variable counter and the two local procedures of add and subtract that processes can use to manipulate it. We can have more sophisticated type of monitors where we use conditional variables. So here we can make the processes wait for a certain condition to become available to execute. So here we're not waiting for simple true or false or 1 and zeros, but we are actually waiting for more flexible conditions to happen before we waken up a waiting or a blocked process. So this is an example with the conditional variables. So we have a monitor called event tracker where processes are waiting right here. So the condition variable here is hungry customer. Okay, and we have two procedures here: the customer enter and the produce burger. So when a customer enters, we have to wait for this condition to become true, which is hungry customers. Okay, and then the next thing, then we have the produce burger, which actually increases the number of resources, which is the burgers, and then it signals the condition variable, which is hungry customer, to allow the waiting process to get its burger, right? Which means that we now have an available burger. You may proceed and get it. So this is a simple example of how to use monitors to get more flexibility. So I'm going to be providing another example of monitors and conditional variables in the scenario of a bank where we have to deposit and withdraw, where we have the deposit and withdraw functions, and we need to wait for certain conditions to be valid before withdrawing. So you have to first make sure that you have available cash before you can withdraw money, right? So in order to do that, you can use conditional variables to synchronize access of different threads and processes.